Sorry I missed class on Wednesday. And sorry this video is coming out so late. I was busy grading projects and stuff. But chapter 22 is significance testing. So we're going to start with a scenario of nightly dishes and four siblings. And Joe, the oldest sibling, says, "Hey, let's put our names in a bag. And whoever's name gets picked has to do the dishes." And then each night after the name gets drawn, they replace it. So it's totally random. Joe's not picked 3 nights in a row. Do you think there's cheating going on? So what's your guess? Assuming that picking one of the four names is truly random, what's the probability that Joe does not get picked 3 nights in a row? Well, there's 3 out of 4 chances he does not get picked. And each night, you multiply that 3 out of 4 times 3 out of 4 times 3 out of 4. So 0.42. There is a 42% chance that he will not get chosen out of 3 nights. So that's probably plausible. What do you think? Could it be true? So let's escalate. Joe, the oldest sibling, is now not picked for 12 nights in a row. What do you think now? What's the probability of not getting picked 12 nights in a row? Well, that's 3/4 times 3/4 times 3/4, 12 nights in a row is 0.032 now approximately, which is 3.2%. So, yeah, at what point do we get suspicious about this? Is it still purely random? What's the probability that he doesn't get picked 12 nights in a row if it is totally random? That's what significance testing does. So, here's another question that we're going to ponder. Suppose that 60% of the population are in favor of a new tax legislation. A random sample of 265 people results in 175 are in favor. So 0.66. That's our p hat. 0.66 p, our parameter is 60%. Our sample size is 265. The number of successes is 175. So following our rule for sample proportions, we know that in this situation, if we did this over and over again, it would be approximately normal distribution with a mean of 0.6 and a standard deviation of 0.03 because we figure out that standard deviation using our sample size. So again, if we know the parameter p, which when we did confidence intervals, we didn't really know p. We were approximating p, but now I know p is 0.6. And the distribution for that is 265 people. So if I took a poll several times, many, many times of 265 people, then the standard deviation would be 0.03, and I would expect the mean to be 0.6. All right, so let's observe this standardized score that's large or larger. So here's the mean, 0.6. The standard deviation is 0.03. So I'd add 0.03 3 times, subtract it 3 times. And from before, we knew from 0.54 to 0.66, that's 95% of the data. And then you subtract that from 100% and divide by 2. So that's our approximation. Now, the z-score, though, is the observation, 0.66 minus 0.60, the observation minus the mean over the standard deviation. That is 2 standard deviations from the mean. When I look that up on a table, it's like the 97.7 percentile, but also you can put that in your calculator. You use that normal CDF, 0.66 is your observation. You put in 10,000 because you want to know everything above that. 0.6 is your mean, and 0.03 is your standard deviation. So here's a new thought. What if we didn't know for sure that the population who favor this tax legislation is 0.6? Our random sample shows 66% of the people favored it. Should we believe this claim that 0.6 is the parameter? Could it just be part of the random sample process? Is it a random sampling error? It falls into the 97.73 percentile, so that's kind of questionable there. But let's say some politician is claiming that we know for sure that the population who favor this tax legislation is 60%. And you're like, I think it's more than that. And you do this random sample and you get 66%. So to do the significance testing, we are going to do some steps here. Now bear with me, it might be a little confusing at first, but we're gonna talk about it. Step 1 is to establish two different hypotheses. The null hypothesis is the population parameter, the status quo, no change in value, just whatever you are initially told, I suppose, is how you could look at it. The alternative hypothesis is a change in the population parameter, not the status quo. Two groups are different. So what that looks like in statistics is the null hypothesis is H with this little 0 down here. That's called null. P, our parameter, is 0.6. That's what we were told. That's what we're going up against right there. The alternative hypothesis for this problem, H with a little a here, we call that sub a, H sub a. P, the parameter, is greater than 0.6. So we're saying, okay, you told me the parameter is 0.6 or 60%. I just did a random sample and got 66%. So I think it might be bigger than 60%. And we're going to test that with statistical significance. Okay, step 2, compute the sample distribution. We did that earlier by stating the mean of the null hypothesis and finding the standard deviation for the sample. So our standard deviation was 0.03. That's what they mean when they say compute the sample distribution. Remember, the standard deviation can change with the sample size. So that's why we use that sample size right there. Step 3 is to collect and summarize the data. Well, we're not going to collect the data because it's already in the problem. It's the random sample of 265 people, and 175 say they are in favor, which is 0.66. Step 4, determine how unlikely the test statistic is if the null hypothesis is true. So in other words, we're finding something called the p-value, the area of the normal curve that we shaded in before. P-value stands for probability. It's so confusing because now we have a parameter, which is the population. We have the p-hat, which is our sample, 0.66, and then we have the p-value, which stands for probability. And our p-value was 0.027 or 2.27%, if you remember that drawing we did here. And don't forget, even if you're doing this on the calculator, you still have to find z-scores on the test. So make sure you know that it's the observation minus the mean divided by the standard deviation. So make sure you know that. Okay, and step 5 is making a decision or a conclusion about that p-value being 2.27. Typically, we say that if a p-value is less than 0.05 or 5%, then the null hypothesis is rejected. This is a cutoff value that we talk about, and we use the Greek letter alpha for that. That's our level of significance is alpha, and normally you will see 0.05. Other scientists for different experiments and things like that might want a smaller level of significance, or higher. It really depends on what you're testing and what your level of significance, what you want it to be. But the standard is 5%. So if the actual parameter was 60%, we should not get 66% just by chance. It's too small of a probability. Okay, so this is that conditional probability that we've talked about before. If the parameter is 60%, then we should not get 66% by chance. Or what's the probability if 0.6 is true, we get 0.66? So it's small. The p-value is very, very small. The probability of getting a 66% is small. Remember that shaded area that we had, it was pretty small. So our conclusion is it's statistically significant that the parameter is actually greater than 60%. We don't believe the politician, basically, who said it was 60%. We think it's higher. Here's a case study that I just made up. Over the last decade, 65% of all American teenagers had their driver's license by the time they were 17 years old. Again, totally making this up. A simple random sample of 474 17-year-old American children shows that 62% of them have driver's licenses. And the question is, does this show that the percentage of all American 17-year-olds with a driver's license has dropped? So we're asking again, our parameter is 65%. We took a simple random sample and got 62%. What's the probability or the p-value of getting that 62%? Did this 65% number in fact drop? So at first glance, it looks like it dropped. 65% to 62% seems pretty significant. But let's see. Could it just be a random sampling error? Because remember, when you take a random sample, you're not always going to get exactly the parameter. You're going to get within so many standard deviations of the parameter. So step 1, you should be writing these steps down, by the way, and memorizing them, is to establish 2 hypotheses. I am going to have you pause the video right now and think about the 2 hypotheses. Which one's the null hypothesis and what is the alternative hypothesis? I will wait. Okay, so the null hypothesis is p equals 0.65, because that is our parameter. That's what we said it's been for the last decade. Our alternative hypothesis is that that parameter is actually less than 65% because we took that sample and got 62%. And the question is asking, does that show the percentage of all American 17-year-olds with a driver's license has dropped? So again, our null hypothesis is no change. It's the status quo. It's what we believe the parameter already is, or somebody's claiming the parameter is. The alternative hypothesis is, yeah, it dropped. Okay, so step 2, write this down. Compute the sample distribution. The mean is 65%. We already established that because that is our parameter. And find the standard deviation. Pause the video and find my standard deviation, please. Okay, standard deviation is 0.02. Remember, you're taking the actual parameter here, not p hat, because we know the parameter. We're not approximating it. Step 3, collect and summarize the data. Well, that's in the problem. 62% of 474 teens. That's our p hat. Step 4, determine how unlikely the test statistic is if the null hypothesis is true. Find the p-value. Again, this is conditional probability. If the parameter is in fact 65%, what is the probability or the p-value that we would get 62% by chance in a sample size of 474? Always make a drawing of the normal curve. I don't care if you're using the calculator or not. Just get in the habit of making your drawing. And to do this by hand, first, we're going to find the z-score. Even if you're doing it on the calculator, the test asks you to find the z-score, so make sure you know how to do that. It's p hat, or our observation, 0.62, minus the parameter over the standard deviation. We get negative 1.5. From the table in the book, this z-score is about 6.68, and there's something missing here. Let me click again. There it is. There's my line. So that's this right here. That's our p-value, that area right here, which is 6.68 according to the table. And if I put it in the calculator, I'm going to the left this time, notice. So I'm going to put in a very large negative number, or very small negative number, however you want to look at it. 0.62 is my observation. Again, 0.65 is our parameter or our mean, and 0.02 is our standard deviation. I get 6.7%. And then it says to make a decision or a conclusion. So what do you think? 6.67%. That's the chance of getting p hat of 62% with a random sample of 474. Is that possible? Well, it is greater than our level of significance, 0.05 that we're using. It's greater than alpha. Because the p-value is bigger than alpha, we determine that it is plausible that a sample size of 474 subjects could, in fact, get a 62% by chance. It's probably a simple random sample error. And so the null hypothesis cannot be rejected. The first one, we had something smaller than 5%. So we were like, oh, wow, that's pretty small percentage. This one is above the cutoff. It's 6.7%. So we have to believe still that the parameter is true, the 0.65. So that parameter remains. We can conclude that it stays 0.65 or 65%. So the first example, the alternative hypothesis was p was greater than a number. So we looked at the right side of the statistic on the normal curve. In the second example, p was on the left side because it was less than a number. So we looked on the left side of the statistic. There's times where we will say p is not equal to a number, and we call that two-sided. And we'll do a sample of this, but it looks like a split. We're looking at both sides of the normal curve. Okay, we are going to take a look at errors we can make. To understand errors that can be made, we'll come back to the problem we just did with the teenage drivers, but the court of law. Okay, so if a person is guilty and they're judged guilty, that's correct. There's no problem there. If they're not guilty and they're judged not guilty, that's correct. But we can have two different errors here. They can be guilty and judged not guilty. That would be an error. They could not be guilty and judged guilty, and that's an error. And we have names for those errors. Type 1 and type 2. Type 1 we call a false positive, and type 2 we call a false negative. So they're judged guilty. That's a positive, even though it's bad. I don't know how to, but it's a positive, and they're not guilty. And then judged not guilty is a false negative because they really are guilty. So it doesn't apply to what your personal beliefs are. It's just like being guilty or not guilty. Guilty is positive, not guilty is negative. So put aside the personal beliefs. That's what it is. Okay, another thing that we use this for is cancer screenings. So a person can either have the cancer or not have the cancer the test is for. It can test negative or it can test positive for cancer. So where would you fill in the chart for correct and errors and what types? Where would they go? Pause the video and write that down. Okay. If they test negative for cancer and they don't have cancer, that's obviously correct. If they have cancer and it tests positive for cancer, that's correct. Type 1 is a false positive. So here they are positive for cancer, but they don't really have it. That's your type 1 error. Type 2 is a false negative. So you actually have cancer and the test says you do not have cancer. So when you get screened for things, like screening for cancers or even pregnancy tests, you can have false positives and false negatives. Like, it happens. There's very small percentages to get on the market with these tests. You have to prove that, most of the time they're correct. I don't know the actual percentages, but it's very, very small percent of the errors that it has. But you will see in these screening studies, like, oh, I know COVID. When we were doing all those COVID tests, you could get false negatives all the time, but it was pretty rare you got a false positive. So a false negative was you had COVID, but it didn't say you had COVID yet. And that was usually people using the tests incorrectly and things like that, not just the test itself. So, okay. In general, the errors we can make. You've got the null hypothesis, your parameter, and the alternative hypothesis. That's like, okay, we're going to test this new thing and see if it's true. The null hypothesis is rejected. The null hypothesis is not rejected. So see if you can figure out where the type 1 and type 2 errors are. Pause the video. There it is. So the alternative hypothesis is true and the null hypothesis rejected. That's correct. Null hypothesis is not rejected. The null hypothesis is still true. That's correct. But here's our type 1 and type 2 errors. And I tried to mix it up a little bit. The alternative hypothesis is true and the null hypothesis is not rejected. That's the type 1 error. That's your false positive, meaning that it's still true that the hypothesis is not rejected. Your type 2 error is your false negative, where the null hypothesis is true, but we reject it anyway. That's your type 2 error. So here is our type 1 and type 2 for the study we did with the driving. 0.65 is the true parameter, and 0.65 is rejected. That's my false negative. P is actually less than 0.65 is true. 0.65 is still assumed to be true. That's your type 1. That's your false positive. Okay, so we have the false positive and the false negative. Now, with our p-value, remember being like 6 point something percent, it's greater than 5%, but it's still pretty close to 5%. So we're pretty close to having an error here. We rejected the null, we kept the null value. We can still say it's true. 0.65 is true. So we are kind of in danger more of having a type 1 error than a type 2 error if we talked about that. So very confusing, I know. Okay, let's practice with spam. It says in a daily news report that the proportion of people who received spam is 62%. In a recent survey by the Gallup organization, 464 out of 692 users said they received spam. Use this information to test the claim at the 0.05 level of significance. Does the Gallup poll show that the parameter is not 62%? So it's not a question of whether it's less than or greater than. It's just saying, is it 62% or isn't it? We're not saying, is it less than, is it greater than? So P, your null hypothesis, is 62%. That's what the Daily News reports, okay? However, the Gallup organization does their 464 out of 692. And so we are going to say that our alternative hypothesis is that parameter is not equal to 0.62%. Or, 0.62 or 62%. So what we're saying this time, we're not saying it's greater than 62%. or it's less than 62%, we're saying it's not equal to 62%. That is two-sided. So we did step 1, which was to find our two hypotheses. Step 2 is the sample distribution. Can you do that? That is finding the standard deviation for that sample size using the actual parameter. So your null hypothesis here, 0.62, that's your parameter. 692 is your sample size. So our standard deviation is 0.02. Next, you figure out your statistic that you're looking at. Well, it didn't tell us in the problem, so we had to figure it out. P hat is 464 divided by 692, which is about 0.67. So that's higher than what we got, the 0.62. Here is our double-sided, two-tailed, I don't know, double-sided, I guess it's called. So our z-score for this, we use the absolute value because we're looking at both sides. So we just consider the positive one. 0.67 is our observation. 0.62 is our mean. 0.02 was our standard deviation. So it is 2.5 standard deviations from the mean, meaning 2.5 to the right and 2.5 to the left, which is why I have the absolute value there. A z-score of 2.5 is about the 99th percentile. On the right side is 1%, the left side is 1%. So the p-score is about 2%. Using the calculator, couldn't get that word out. I have 1 minus the normal CDF, 0.57, because it's going to go from 0.57 here to 0.67 here. And our mean is 0.62 and our standard deviation is 0.02. So when you put this in your calculator, you have to subtract that from 1 because you're only looking at the tails. When you put this in your calculator, it'll give you the area between these two numbers. So you have to do 1 minus that number and get your 0.012. So the p-value is 1.2%. That's lower than 0.05%. The null hypothesis is rejected. The proportion of people that receive spam is not equal to 62%. Again, we didn't say whether it's lower or higher. We were just testing to see if it is not 62%. So we have lower, we have higher or greater, and then we have not. So one's on the right, one's on the left, and there's a two-tailed one. So remember though, when you do this, you are not looking for the area between 0.57 and 0.67. You're looking for the tails. So you have to do 1 minus that because the area under the curve is a probability of 1 or 100%. So you're looking for the tail end, so you have to do 1 minus that number right there. And that's all I have for now, and we'll talk more about this in class on Monday.